Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. After talking about special polytopes in general dimensions in the previous video, we will now talk about the general case of polytopes in a fixed dimension, namely dimension 2. We will discuss Pick's theorem. Pick's theorem is a famous theorem from the late 1800s. It says that if I have an integral polygon, so a polygon in the plane with integer vertices, then there's a relation between three quantities, namely A, which is the area of the polygon, I is the number of interior integer points, and B, which is the number of boundary integer points. So for example, this septagon on the right has 15 interior integer points. It has 10 boundary integer points, and so Pick's theorem says that in this case the area is 15 plus 1/2 of 10 minus 1, so it's an area of 19. If you've never seen Pick's theorem, you should be amazed at this point, because it gives a way of computing continuous data of the polygon, the area, in an entirely discrete fashion. So the quantities on the right over here are quantities that I can count. And so at first, this might seem counterintuitive that you can compute continuous data of an object entirely by a discrete process. The reason why this works is there's a strong condition here, namely the input, if you want, the object has a discrete fashion too, namely this condition that I need to have integer vertices is a strong condition. In the book, we give a proof of Pick's theorem, and my goal in this video is to give you, number one, a slightly different proof, because it points to something that we will use later. And number two, I want to discuss which concepts that are hidden in this theorem can be extended to higher dimension. Let me start with the latter. There is a convenient way of computing volume of a simplex. So a simplex is a d-dimensional polytope in general with the fewest number of vertices, that is d plus 1. If you give me a d-dimensional simplex that I call delta here, what I will do is form a matrix out of these vertices by subtracting one vertex from the other d. So this gives me a d by d matrix. And you might remember from your linear algebra class that the volume of a parallelepiped spanned by d linear independent vectors is the determinant, it's rather the absolute value of the determinant of this matrix. And so it's a short step to go from a parallelepiped to a simplex formed in this way. Namely, in this case, I take the same kind of determinant, absolute value, and I divide by d factorial. what I wanted to show is there's in dimension 3, the kind of relation that's given by Pick's theorem is too strong. What I mean by this is the following. I'm giving you an example of a three-dimensional simplex. It's a tetrahedron. So I'm thinking of this as given by the vertices. So I have a vertex at the origin, and then a vertex at distance 1, let's say, on maybe the x-axis and the y-axis. And then I have a vertex whose coordinates is 1, 1, and then some parameter h. So h tells me how high up this fourth vertex is. If there were such a relation as Pick's theorem in 3 dimensions, well, the analog of area is the volume. Maybe let's write this as V. And then, of course, I could again count interior integer points and boundary integer points. And in this case, the volume, if you think about what we just wrote down, is given by 1/6. So D is 3 here, so it's 1/6 times this number h. There are no interior points, and there are precisely 4 boundary points, no matter what h is. So this tetrahedron is constructed in such a way that it has very few integer points. And now you can see what goes wrong with the relation in Pick's theorem. So I have constants over here, but I have a volume that depends on a parameter, and I can change this parameter freely. And even if h is an integer, I can make this volume as large as I want. And so that means a relation between 3 quantities, like in Pick's theorem, is too much to hope for. We will see in the next chapter that there is a relation in 3 dimensions, but it will have to involve one more quantity. It's kind of like going 1 dimension up. You have to have one more parameter. And if you pick this parameter correctly, lo and behold, there will be a relation somewhat analogous to Pick's theorem. So now let's go back to dimension 2. And I promised you an alternative proof of Pick's theorem. So the first thing that we do in the book is we suggest that Pick's theorem can be proved inductively in the following way. If I have a polygon like the one on the right, I can dissect it into 2, maybe like this. And then we show in the book that if you now know that Pick's theorem holds for the 2 smaller polygons, we can sort of glue them together. We can glue this identity together to then prove that Pick's theorem holds also for the original bigger polygon. In the book, we then reduce this to a case of sort of certain rectangles and certain triangles. But what I want to show you now is a different reduction. So what I will do is I will just keep adding new subdivisions. So maybe something like this next, and then maybe something like this. And I will keep going until I'm running out of integer points that I can use to subdivide things. So maybe we should do that in a more regular fashion and decompose our given septagon, let's say like this. What I have done here is I kept subdividing. So what that means is I necessarily end up with triangles. So these are all triangles. But even with triangles, I might keep subdividing. So what I'm doing here is I'm getting down to a point where my triangles are minimal. in a sense that the only integer points in each triangle are the 3 vertices. So what does that mean? That means that if I have such a triangle, so maybe I'll call this delta. So again, so delta is a triangle with this property, then, well, we just said there is no interior point, and there's precisely 3 boundary points. Then what we need to prove if Pick's theorem is supposed to hold, we need to prove that for any such triangle, the area is 1/2. I claim this is an exercise, and in fact, it's one of the exercises that was in chapter 1. The process that we described here, this object of decomposing, in this case a polygon, is called a triangulation. It's a good name. And in fact, this is a special triangulation. It's called a unimodular triangulation. That name comes from the following definition. This is again sort of in general dimension. So if I have a simplex whose vertices are integer points, then the determinant that you see here in this volume formula has to be an integer. And so the minimal possible volume of a simplex is 1 over d factorial. And those simplices that have this minimal volume of 1 over d factorial, those simplices we will call unimodular. And so what you saw in this previous slide is a triangulation of a polygon into exclusively unimodular triangles. I wanted to mention that because this is another special thing in dimension 2. So you can convince yourself that what we did for this septagon, you can always do. Every polygon, every integer polygon has a unimodular triangulation. But this is again something that sort of fails in higher dimension. And I'll give you the sort of simplest example over here. So you see a picture here of a tetrahedron that's embedded in a unit cube. So again, maybe let me make this here the origin. Then I have a simplex whose vertices are the origin plus the 3 points. Maybe this is the point up here, 1, 0, 1. So the 3 points that have precisely 2 entries that are 1 and the third entry that's 0. Okay, let's compute the volume. So, well, number 1, I want you to note that this tetrahedron has no interior integer point and as boundary points only the 4 vertices. Okay, so in particular, we cannot triangulate it any further. There's no way to decompose this into smaller lattice polytopes or lattice simplices. But I claim this simplex is not unimodular. And to see that, I think of the simplex as embedded in the unit cube that you see here. I can think of this tetrahedron as being obtained by cutting something out of the unit cube. Namely, there are sort of 4 tetrahedra that you take away from the unit cube. Here's one of them. And there's one sort of to our front and then 2 in the back. So, and I claim, you can check this, those 4 tetrahedra are unimodular. So what does that mean? So that means that the the volume of my tetrahedron inside is 1, that's the volume of the unit cube, minus 4 times the volume of a unimodular simplex in dimension 3, that is a 6. And so this volume will be a third. So again, what this means is that my tetrahedron in the middle is not unimodular, but it's something that I cannot triangulate any further, at least not into integer polytopes. And so the picture that you've seen in dimension 2 is that any sort of polygon can be triangulated into unimodular triangles. This picture does not hold in dimension 3, even for some very, very simple polytopes. We cannot triangulate this in a unimodular fashion here. At any rate, we will still use triangulations, and they will still be very useful for us. But what this suggests is that we need techniques beyond sort of this unimodular philosophy.